Hello students, we're going to look at how to use a Taylor series to represent a function. So far, we've been using a Taylor polynomial or Maclaurin polynomial to approximate values of a function at a particular x value. But it stands to reason that if you increase the number of terms in your polynomial, you're going to get a better approximation. So if we increase it to an infinite number of terms, we should theoretically get the exact value of our function. And that's essentially what we're looking at today. We're going to take a series with an infinite number of terms and get an exact value for our function. So for a Taylor series, the rule is the same as for a Taylor polynomial. If you look on the right side there, it's f of c plus f prime of c times x minus c to the first, on and on and on. But the two things that you have to think about here, that you have to remember when we're talking about series, is that number one, our series value is going to be the exact value of the function. It's going to be equal. And because it's a series, it can be represented in summation notation. Now that thing after the sigma symbol is just the rule for the nth term. If we're going to infinity, we need to write out a rule for an nth term so we have something at the end of the line for our expanded series. All right, remember, if the center of the polynomial is 0, it is called a Maclaurin polynomial that works with the series as well. So there's a few of these things that the College Board uses over and over and over again. They do a function, e to the x, sine of x, cosine of x, and 1 over 1 plus x, where they'll approximate that with Taylor polynomials, but they'll also do this Taylor series expansion of those functions. And these, we're going to have to memorize the patterns so that you can write these out really quickly. The patterns are really easy to use, and we'll do the first two together here, but then I'll give you the rest of them in a reference table. And you'll see it's not difficult to put together what the differences between the patterns are. So we're going to look at a Maclaurin series that's centered at x equals 0 for e to the x and also for sine of x. And just remember the rule for a Taylor polynomial, of which Maclaurin is a special case, is that rule up at the top of the screen there. So if I write out the first few terms replacing all the c's with 0, I get something that looks like that. Now I'm going to go in, I'm going to do this specifically for e to the x. So remember, all of the derivatives of e to the x are e to the x, and when I replace all the x's with 0, anything to the 0 power is equal to 1. So my e to the x term is going to wind up being equal to this. And I left a little dot, dot, dot at the end there because this is a series. We need a way of representing the nth term. So if you look at the pattern here, it looks like the exponents for x and the factorials in the denominator are always the same number. So all I need to do is write x to the nth over n factorial. Fairly straightforward. Now you're going to have to know how to write out that expanded series from memory, but you're also going to have to represent it in summation notation and to recognize that because they're going to do that. So that's fairly easy here. We're just going to take that nth term rule, x to the n over n factorial, and just put it after a summation symbol. The thing that's different with this from what we've done so far is that we're not starting at n equals 1 now. We're going to start at n equals 0. And that is really just a little technical thing to try to match the first term when we write this out without any real difficulty or special work involved. All right, so we're going to look well, like I said, you have to memorize those two. We're going to look at the Maclaurin series for sine of x, but before we do, remember the sine and its first few derivatives look like this, and then the pattern repeats over and over and over again. And if I substitute in an x value of 0, something interesting happens here. Sine f itself and all of the even numbered derivatives become equal to 0, which means that any term that has a sine in it is going to go to 0 as well. So when I represent sine of x as a Maclaurin series and I write out my terms here, all of the even numbered derivatives and f are going to have a 0 in them. And when that happens, we can rewrite it without the zeros, and we're going to get this pattern showing up. So there's two things to pay attention to here. Number one, all of the degrees of x are odd. Right? The factorials are going to match those degrees. And there's an alternating pattern that's happening here. We're going from a positive to a negative to a positive to a negative. So when we write out our rule for our nth term, we're going to need a -1 to the nth power to do that. Also, because we want only odd degrees of x, if we wanted something in terms of n that will give us an odd degree, we're going to need an even degree, which is 2 times n, either +1 or -1 to get us to an odd number. We're going to choose the 2n plus 1 option here. And once we write that out, we just have to put it in summation notation starting at n equals 0. And again, you're going to have to memorize the expanded series and the representation of the series in summation notation. It's easier than you think. Like I said, you're going to have a table with all of this stuff while you're practicing for the test, not on the test itself, unfortunately, though. So I'm going to give you all these values here, and I will post this table in Google Classroom for you as well. For right now, don't worry about that last column, the interval of convergence. We'll look at that in another lesson. You just need to know how to expand the series and how to represent it in summation notation. So the two that I want to kind of focus in on right now are the sine and the cosine ones. For sine, notice that all of the degrees are odd. There they are. So when you represent that in your summation notation with your nth term, the power of x has to be either 2n plus 1 or 2n minus 1, and we go with the 2n plus 1 option. For cosine, all of the degrees are even exponents. So we just need a 2n power of x in summation notation. So let's look at how to represent functions with these things, and you'll see how there's a slight change here. Instead of sine of x, it's now sine of x squared, and instead of x squared, instead of e to the x, it's x squared times e to the x. So what we're going to do, we'll start with the sine, remind ourselves what the expanded series looks like for sine, and we'll just write out the general rule for that over here, x minus x cubed over 3 factorial, on and on. It's going to look like that. Now, the only real change we have to make here is that everywhere there's an x in our series, we just replace it with what the input for sine was, which is x squared. So all of those x's are going to get replaced with x squared. And now when you have a power raised to a power, remember you multiply the exponents. So it's going to look like that. Now that's essentially your expanded series. You just need a rule for the nth term. But if we can commit that rule to memory, remember you have the alternating -1 to the nth power. These are odd powers of x in the original expansion, so you need that x to the 2n plus 1 power, all over 2n plus 1 factorial. Right there it is in the table, right over there. All you have to do is replace x with x squared. Right? That x gets replaced with x squared, right down there. And a power raised to a power, you multiply the exponents, so that's going to become x to the 4n plus 2. Everything else stays the same. All right, fairly straightforward. I'm just going to remind you of the pattern for e to the x, because that's the one we're going to use on the next problem here. E to the x is one of the easier ones, 1 plus x to the first plus x squared over 2 factorial. You just keep going on and on as you go. So there's the rule for e to the x, including the nth term, x to the nth over n factorial. And the only thing we have to do here is we have to multiply every single one of the terms in the expansion for e to the x with x squared, because the function is the product of x squared and e to the x. So we're going to multiply each one of those terms by x squared. We're going to get something that looks like that. And remember, if I multiplied that last numerator, x to the nth, by x squared, when you multiply powers of the same base, you add the exponents, so that gives me the x to the n plus 2. And once I have that x to the n plus 2 over n factorial, then I can easily write out my summation notation. And that's the game. That's the whole thing. So I am posting a Delta Math assignment that has a series of these problems where you'll have to use the expansion rules for e to the x, sine of x, cosine of x, and 1 over 1 plus x. And change your inputs, multiply them by an x squared like in the last example we just did, and come up with a function representation as a series to give yourself an exact value with a polynomial instead of whatever the original function is.